So thanks for coming. Hope you have a good lunch, and hope you have hopefully this will be a fun session. So we're going to be talking a little bit about AI as a service. And I want it to be, or I'll try to make it as interactive as possible. So I'm pretty sure, how many of you actually, are in some way working with machine learning or data science or AI today? Okay, quite a few, right? And I think a lot of you, some of this talk, at least earlier on, is going to be, to some of you, very obvious, and to some others, hopefully somewhat interesting. So why bother with AI, right? You've obviously heard the hype, and you've obviously seen everybody talk about AI constantly. But why should anybody care about artificial intelligence or machine learning? By the way, I use these terms interchangeably, so we shouldn't get stuck up on machine learning versus data science versus AI here. But the most important thing when it comes to, like, say, any company or any organization, is AI can completely transform the customer experience. So there are many, many places throughout your customer experience where you can imagine applying AI or machine learning and transforming it to basically increase customer engagement, revenue, and so on. Business process. You've seen this in especially large companies like Samsung. There is a lot of business processes which are currently at play in companies like this, and to automate those business processes makes our life much easier. And the most fun and I think challenging part of AI machine learning is planning and forecasting. To tell you the truth, forecasting is very difficult. If you could actually forecast the future, for example, if we could forecast who would win the Iowa caucuses today, we could possibly make a few $1 million just on betting or something. But forecasting is another key part of AI and machine learning. The other reason to worry about this is just history. If you look at the top 5 companies in the world today, Amazon, Facebook, Google, Apple, Microsoft's missing. Looks like, for some reason, I should put Microsoft on here. Facebook, of course, everybody's heard of this. YouTube. The biggest actual Google innovation that nobody talks about is this thing called YouTube Next. So if you guys are YouTube users, you will know that once you play YouTube, the next YouTube video will start playing automatically. And that particular innovation basically has gotten YouTube to be the most used and the most interactive site in the world today. And when Facebook and Google fought with each other, the YouTube Next is what gave them the upper kind of hand. And finally, of course, you've heard of Apple. So, next part is all of these people have used deep learning, and they've become really big, and they've used it in smart ways. Still, if you go to a traditional company, a lot of people will be like, deep learning, who cares about deep learning? We actually only care about classical machine learning, or we care about like trees and stuff like that. And here's our point of view, why deep learning matters. Because today, that's where all the research is. So if you think about it, if you go to any conference, 85, 90% of all research papers are to do with neural nets and deep learning. Very few papers deal with kind of classical ML. The other part of this is you don't have to know which features matter. So for some of the people who are kind of more AI, ML savvy here, you'll know that most of the time you have to worry about which features you want to include in your ML model, right? With deep learning, that's a little bit less of a problem. Still a problem, a little bit less. And of late, especially 2018, 2019, we've seen that deep learning almost always beats classical machine learning in most cases. So the only case where it doesn't beat it is when you have less data, right? And this less data is very little data. Typically, we like to say 50,000 or more data points, you want to go into the deep learning kind of territory. So, and I would say most enterprises, especially Samsung, definitely has enough data for you to really look into deep learning over any type of other learning algorithm. It shouldn't be a progression. The other thing I've seen is people start with saying, oh, let's do something simple, and then let's go do deep learning. Deep learning is actually quite simple. There are a lot of really easy to use libraries today, and you could really dive into deep learning directly. And most of all, it's clearly obvious, I think, for the people who are the naysayers or kind of like skeptics. There has been a recent study done, and it was done by McKinsey. They talked to 1,100 different companies across the world, and pretty much everybody has said that actually AI improves their bottom line anywhere from 30% to 128%. So if you want to pick that project where you're going to have this bottom line impact and hopefully potentially even get promoted many levels, I would say pick an AI project. Well, you know, okay, so what is all this hoopla about deep learning when it was actually invented in 1943? So it's not something new. The reason why it didn't take off was that these networks were very computationally expensive. So does everybody have a little bit of an idea of what deep learning is? Yes? Or do you want me to give you like a 2-minute summary? No? Okay. So, yes. Okay. So 2-minute summary. So what basically happens is, what we're talking about is taking a bunch of data, right? And basically in that data, typically, I'll give you the simple version. Typically, let's take a very a classic example. You have a bunch of pictures. This is the classic vision example. Let's say 1,000 pictures. 500 of them have cats in them. 500 don't have cats in them, okay? And then what you have is a deep neural network. And what that really means is nothing more than these neurons which are connected to each other. Now, what's a neuron? Neuron is nothing more than a mathematical function of sorts, excuse me, which has a weight or a bias. So what does that mean? All that's happening is take these pictures, and we take each of these pictures and make them into a mathematical vector, okay? What that means is like a bunch of numbers. So each picture is represented as a vector, and each of these numbers are then fed into this neural network, and each neuron actually multiplies the numbers by something that's called a weight, or it adds something to the number, and that's called a bias, right? So each neuron adds a weight, multiplies by weight, and adds a bias to those numbers. And then after you push it through a bunch of these neurons, hopefully I have a slide here which you can take a look at. If I don't, I'll have to just explain it. But anyway, I don't. Okay, so after you push it through the bunch of neurons, you get a result. That result has to be whether the picture has a cat or not, right? So basically, you're taking these pictures, turning them into numbers. The result is also in some sort of a number format. And the idea is you have to train the neurons, or train the neural net, so that given all the 1,000 pictures, and telling the neural net 500 have cats and 500 don't, it learns what kinds of pictures or what kinds of features a cat has. So basically, it's just like your brain does. Like if you're a baby and you're like, here are 5 cats, here are no 5 cats, right? And then the 6th time, if you look at a cat, what is the baby going to say? Oh, that's a cat. That's pretty much it, except we're doing this with math. And we're basically converting these pictures into numbers, and these numbers have some weights and biases added to them to get a result. I can go into this a little bit deeper, maybe in some of my slides which go by. But the idea there is basically trying to recognize or predict something which you haven't seen before by using a lot of training data. So before, to be able to train this machine deep learning network, you would need lots and lots of compute. And you also needed a lot of example data. And what happened is, obviously, throughout the decades, so to speak, the internet was born. And with the internet was born lots of data. Like Google, Amazon, Facebook, all of these companies started having a lot of data. Of course, there's a very interesting challenge which happens every year called the ImageNet challenge. This is very key. If you're into like AI or deep learning, you probably want to know about the ImageNet challenge. And the idea behind the ImageNet challenge is that it's a massive data set of 14 million images with 21,000 classes. Classes here mean nothing more than like objects or labels. Like for example, Black Widow is a class. Tiger or leopard is a class, right? Mushroom is a class. So there are 21,000 of these classes with 14 million images. And the challenge basically is to come up with an algorithm which predicts most of these classes. So first you train on some part of the ImageNet, and then given kind of data which it hasn't seen before, the algorithm has to guess which object the image has. So imagine training a model and then giving the model an image which says, what does this have? And it'll say, oh, it has a leopard, or it has a cat, or it has a window, or what have you. And till then, basically, there were lots of models which were being used, and there was a lot of image processing models which people were trying to win in this competition. And in 2012, these 3 guys got together, and one of them is the father of deep learning, Geoffrey Hinton, and came up with a neural net which basically completely blew everyone else away. So their error was much, much lower than anybody, the second runner-up, right? And that's when basically the revolution of deep learning started. So in so many ways, you could almost think of the rebirth of deep learning in 2011, 2012. And after that started, there was a whole host of new inventions. And really, the key things that you will hear again and again, other than vision, and this example of recognizing images or doing bounding boxes on images is vision, is text. So Watson by IBM actually competed on Jeopardy and won. Jeff Dean and Andrew Ng reported an experiment where they showed how it can find things in a large, where a neural net could basically respond to images which haven't been labeled and look at those images and say there are cats in it. And all of these were seminal kind of changes. But if you look at the last 4 or 5 years, there's been a lot of progress in deep learning. At the same time, AI in enterprises, it's not like enterprises haven't thought about machine learning on data science, right? If you look at that in parallel, it hasn't, because it's still 6 years old and sometimes enterprises take like a decade or more to adapt, there is still it's still early days. So people very often use statistical models. They're still in production, especially in production. Very, very often we use heuristics. In fact, even startups use heuristics, right? Because it's very simple to use a rule-based system. And then in a lot of cases, you have your data, but it's trapped in some software system like SAP or Oracle. So the current world as it stands is quite early. So mapping where if you look at the same survey, only 20% or 21% of the 1,100 respondents have said that they have AI embedded in all parts of their business. What this means to most people is it's time to start thinking about things. It's time to start starting new projects where you can actually embed AI. And that's good news, right? Because there's an opportunity. While it's still early, it really, really helps you with actually not only just keeping up with the Joneses or keeping up with your competition, but actually leapfrogging ahead. There are multiple examples where you will see, and I gave you the YouTube example where there was a really big fight between Google and Facebook on video, where you will see that you could use kind of a transformative AI model, which will give you anywhere, like I said, between 50 to 120% increase in engagement, which means you just literally leapfrog ahead of your competition. So there has been a lot of cases, at least around 30% of the time, where they've said, this has really helped. But what is the biggest roadblocks to AI, right? Today, the first roadblock is actually picking the right problem to solve. If you look at all the stuff that you're doing, I guarantee you, every one of you people, if you are in some way involved in a product or an engineering team, there is some application of machine learning in what you're doing. There's just no doubt about that, right? But then you have to pick the right problem to solve. If you end up picking a problem which is too difficult, or if you end up picking the problem where you have no data whatsoever, you can be fall into all kinds of problems, and you can be stuck in the POC phase forever. Second is shortage of talent. And this is key. It's not just shortage of science talent. To build an ML system in production, you need 5 different types of people. You need back-end engineers, you need data engineers, you need data scientists, sometimes you need research scientists, you need data analysts and project managers. Basically you need a lot of different people coming together, and they all have to work together. When is the last time you've seen lots of different functions working really well together to get something going? It's difficult. And today, it's actually, there are lots of tools, there's lots of noise in the market, but very few tools actually work. So there's lots of hype, and there's no real kind of answer. So if you look at the right problem to solve, that's the first part. Here's what I would recommend. I would recommend looking at the data that you have. All AI, machine learning, everything depends on data today. I mean, in the future, maybe it won't depend on data, but today it depends on data. So you want to see what kinds of data do you have? Language, vision, or tabular data, typically. Most cases, you have tabular data. Not that, while some people do have language or vision data, it's not entirely clear how they can use it in a good way today to improve their business process or their customer experience. The other part of this is labeled versus unlabeled data. So the people who don't know what that is, it's very simple. If you have data which, like the image example I gave you, if you have 1,000 images and you don't know which ones have cats and which ones don't, that's all unlabeled data, right? If you know which ones have cats and which ones do, then you have labeled data for cats specifically. Now, some of them might have windows, or some of them might have doors in the pictures, but as long as you don't label them, that's all unlabeled. So there are 3 types of learning, which correspond to the type of data that you have, labeled versus unlabeled. Supervised, that's the one which everybody kind of uses nowadays. Almost 95% of things in production, I would say, is supervised learning. So that's a common thing. Semi-supervised is coming into fashion of late because many people don't have labeled data. And unsupervised learning, I would say, in the next 3 to 4 years is going to become really, really a big deal. I like to highlight tabular data because most people understand how vision or language works. Vision is recognizing objects, like I said. And also, it gives you the computer's eyes. So where vision is most useful is autonomous driving and robotics. So if you want to have any robotics or autonomous driving application, you can't do that without perception. Perception is vision. Second is language. Language, you think of things like chatbots, you think of things like customer service experience, and that's where language gets used the most. Sentiment analysis, all that sort of stuff. The problem with language is NLP is not very, I would say, not completely production ready. It's there, but not quite there. Because if you really let a chatbot answer all questions and then run away, basically if you just say, hey, I'm going to basically tell my customer service team to start working on something else. Let's not worry about responding to customer service requests. Let this AI bot do it. It's not going to work. So NLP is not quite there. But the other thing which people forget is machine learning and AI can also be used for tabular data. And there's a whole bunch of different use cases there, all the way from fraud to user churn to forecasting, recommendations. And the other really, really interesting thing which is coming out of, I would say, the labs and into production is anomaly detection. Looking at anomalies, whether it comes to anomalies with security. So you're seeing something weird, the AI can alert you. When it comes to pushing things to production, if you see something going wrong with your production workloads, with your AWS workloads, the AI can alert you. Today, the top use cases, cybersecurity, customer service, and predictive analytics, right? Cybersecurity is one area where things have gone into production. It's a very lucrative industry. If you guys are thinking of a startup, this is some place to start, but it's very, very crowded, but still there is room. Customer service, is something which a lot of people have tried. It's still, I would say it's still 2 years away, but it's obviously a place where you can imagine natural language processing coming into use a lot. This one is probably the most used example in enterprises today, predictive analytics. And this is the idea of doing risk scoring, spam scoring, finding anything where you have a target variable, which is a dependent variable, and then kind of predicting that variable based on other independent variables, right? Anything where you think that there is some way you can predict something, you want to think about predictive analytics. Based on A, B, and C, predict D, that's where you're thinking about predictive analytics. The other big issue is shortage of talent. Now, it's weird to come to Samsung and say, hey, there's a shortage of talent in AI. But I will tell you that Google thinks there's a shortage of talent in AI, and I'm not kidding. Or Amazon thinks that. Why? Because there are lots and lots of problems to solve. And the amount of talent you require to solve one problem is very, very high. So, and the reason for that is, as I mentioned, to put this into production. Now, lots of people think, hey, I've done a POC, I've got a model, I've got a notebook, it works, I'm done. You're not done, you just got started, right? Because that thing is not in production, it's not getting retrained, you don't have data pipeline set up, you don't know how the model is going to behave in the wild, you don't know what happens after some time, what happens if there's model drift, what happens if the model gets worse. So a lot of these problems have to be addressed before you can put something into production. And I'll give you another example. The personalization team in Amazon has 1,000 people, right? And so, or the team at Facebook, the newsfeed team has another almost 1,000 people. So a lot of people think, all the big companies by far think that you need a large number of people to basically do anything, get anything done. And I'm sure at Samsung, you guys are solving some hard problems, but how many people do you need for each problem? You probably need 200, 300, a lot of people to solve these problems. So you also need data pipelines that are reliable and can get very complex. So it can get very hairy. You'll have to pick multiple data sources. You're going to integrate those data sources, get them all together. So even if you're a large company, you want to be able to do things more efficiently. The other thing is too few tools actually work. So this is a crowded space. There are lots of tools. There's lots of open source tools. Open source can get very tricky because, you have to run it, you have to monitor it, you have to do everything, and it gets painful. I'm a big fan of Amazon SageMaker, actually, but it doesn't address some of the data management and wrangling issues I just spoke about. Same with, generally, a lot of the cloud organizations you've seen have, grown too big, and services are sometimes incomplete, and they will, however, fix some of these gaps. But at the moment, there is no winning tool yet. So there's a big opportunity, we think. And also, regardless of that, regardless of we, meaning Reality Engines, who is a small startup, the whole space, I think, has this big opportunity. And a lot of people are making headways and strides in this space, and that is AI as a service. And what does that mean? Basically, we're saying a set of plug-and-play AI services for developers, or it could be some startups building AI as a service. Obviously, the cloud vendors are also going to be building this to some extent. So what is the layer cake approach to APIs, right? When you think about services today, and I don't know how many of you use APIs? Okay, quite a few. So you know exactly what APIs can do, right? And there are different levels of abstraction of an API. Whenever you're building a system, I would strongly encourage you to think of the 3 levels of abstraction. The first level being, here is a simple way to get my task done. So if you're a developer who can't be bothered about the inner workings of a system, you want to be working on the top layer. If you want to go to want to do more customization, and you need more flexibility, you go to the middle or the bottom layer. And this way, you can basically get all kinds of people, both the newbies, the level 1 people, and the level 3 people kind of really using your API, and the API becoming more all-purpose. Okay, so let's say you wanted to build your AI as a service, and you want to start off today. What would you want to build? You want to build these 6 modules. You want to build a dataset exploration and cleaning module. You want to build a feature extraction and selection module. And basically what's happening is the data is coming in here. You're processing and cleaning. You're taking out the most important features. Sometimes you would need to augment your data. And we'll talk a little bit about that. I don't know how I'm doing on time, actually. Anyway, so, OK. So, and then we can do model training and testing, and then model hosting and explainability. So anytime you're thinking about building an ML system in production, you'll want these dark blue boxes. There's no question. You can't build an ML system in the world without those dark blue boxes. The light blue is kind of icing on the cake. If you want that too, that's great. You don't need it. And basically, data in, streaming, or any kind of data in a warehouse. So if you have a lot of data sitting on a S3 bucket, on a warehouse, in a database, the data goes into the system, and prediction and inference on the other side. OK. Having said that, there are still a lot of hard problems that you will have to solve if you want to put systems into production. In some cases, these problems are a non-issue because there are simpler cases, and there are some cases these problems are a bigger issue. So the first one is training with less data. When you don't have enough data, you can use a lot of techniques in deep learning to augment your data set. I'll kind of breeze through a few techniques here, and they're very high level, but you will need to use one of these techniques. And that's where we had that augmentation as a module there. The second thing, which is really interesting, is what we call AI-assisted ML. And the idea there is AI is building the model on your behalf. So the first pass is done by the AI, and then you get to tune, tweak, and customize it. And the third is explanations, right? The explanations idea is basically explaining why a particular prediction is what it is. A very common problem you have with deep learning is that you get a prediction and you don't know why it made that prediction. Let's take YouTube again. You suddenly see some video and you're like, I have no idea why it showed me this Trump video. I'm a Democrat, it's showing me Trump videos, it's weird. And that happens. And you need some way to explain it. Now, techniques to train less data. Again, I'm just going to touch on these techniques because we're running out of time. You can obviously Google them because there's a lot of data, as you can imagine, on Google around a lot of these topics. The first one is dataset augmentation, and that's the idea of adding synthetic data to your original data. So if at any point you're working on an AI model and you feel like there isn't enough data, this is a technique you could use. It's a very, very new technique, so you'll have to go figure out how it'll work for your use case, but it's something which works. The second is something called learning to learn. Now, this is a very, very exciting part of AI. If you want to do a PhD, instead of wanting to start a company, you want to go off to school instead, or you want to be in Samsung and still go to school, meta learning is what I would recommend as your PhD topic. It's the most exciting part of AI today when it comes to research. Here, we're building models which learn to learn, right? So if you learn to learn, then you can actually easily build a model with very less data. Transfer learning, it's very simple, like how your brain works. I learn some task, but I can transfer the learning from that task to another task. That's literally transfer learning. Logic rules, this is, initially I mentioned that most companies have heuristic-based systems. Imagine if you had a heuristic-based system, but you also have a machine learning or like a system which trains on data. You want to combine them. Of late, there's a lot of work around combining logic rules and deep neural nets. This phase I'll go through very quickly. This is the dataset augmentation phase. This is a simple example here. You take a cat. You want to you have only one cat picture. And now, that's not enough to train your network. What do? You can take the cat and turn and rotate the cat in several ways. And suddenly you have 7 cat pictures. So simple things like rotating or changing pose or making kinds of little changes will help you enlarge your data set. This was something which people would do all the time. Now with a new technique called generative adversarial networks, you can actually do this with a neural net. So you don't have to actually go look at the picture and change the pose, which is actually quite hard to do, and it's domain specific, right? You can actually use another neural net to create fake faces, and this is where the deep fakes comes from. You've obviously all heard of deep fakes, right? So you can take real faces and you create generated faces, and what really is going on in the background is there are 2 neural nets, and one is creating the fake samples, and the other, the discriminator neural net, is checking to see if the fake sample is as good as the real one. Basically, the discriminator is basically trying to call the fake sample fake and call the real sample real. And the generator's job is to fool the discriminator, right? That's what's happening in the back end. So I'm going through this fast, but the overall point that you have to get is GANs, which is generative adversarial networks, can create fake or synthetic data. That synthetic data can be used to augment your real data and in turn create a bigger data set. Another example where this row here is real, this is all fake. So you can create fake data for anything pretty much and improve the performance. Meta learning, the one is the learn to learn. Basically, you have a model which teaches another model. And again, the approach there is you just need a few examples to teach this kind of model new tasks. So let's say you have a specific task which is to classify cats. And you have a new task now to classify rats. I'm just making this up. The new task is very easy to teach if you have a meta-learning model and you won't need 1,000 examples of rats, you'll need 5 or 10. Another approach is transfer learning. This is very, very common. This is the one, say, Google, Amazon, Facebook, Microsoft, everybody uses. I think all the cloud providers have a way for you to use one of their pre-trained models. So what they'll do is they'll train their model on their large public data set, and then you can then train that pre-trained model. So it's like training on a trained model on your small local data set. So a classic example of that could be, I have a pre-trained model from Google which is trained on all the images in the world, and I have something which is very specific to Samsung phones, right? And I want to train a computer vision model which looks and identifies every single model of every single phone. You would use transfer learning. In the transfer learning problem, the neural net that I spoke about, you only have to retrain the last layers of the neural net. And with transfer, you get a much higher performance than without transfer. the last way of like getting to better models is using logic rules, as I mentioned. So when you have some prior knowledge of some particular system, take, for example, a recommendation system where you can say, hey, most women like high heels. So when you have a women customer and she searches for shoes, you want to show her high heels. But if you have a guy customer and he searches for shoes, you don't want to show them high heels, right? Or you want to show them boots or sneakers. How do you incorporate that rule into your system? So today, for example, there are just rule-based systems. And if you use a neural net, it does not incorporate the rule. But of late, there has been a lot of really good research where you can impose constraints on particular data sets and then train a neural net. And by doing so, you're basically incorporating both the rule and the example into a model. This is very, very powerful, especially in a lot of like enterprise use cases, using modifying the loss function to impose a constraint. This is some of the research we've done in our company. A lot of our focus is training on smaller data sets. So some of the things that you're seeing is actually some of the research we've done. You can see that you can get improved accuracy, especially if your data set is noisy, by using the rules. It's very classic to see enterprise data sets being very noisy, right? I mean, if you guys have looked at any log data, it's never clean. It's always noisy. And the easy way to kind of like overcome it, okay, I shouldn't say easy, a way to overcome it, but it's not that easy to do, is to use constraints and rules. For example, you could say, this particular data combination should never occur. That's a constraint. So when it sees that data set combination in the logs, it knows to ignore it. Okay, finally, after we've figured out how to deal with less training data, we want to now create the best model for our data set. So we've got our data set. So we figured out how to deal with less training data. What do? The best and the easiest way to do it with neural nets is to do a search of neural net architectures, right? And that's a very popular research topic called neural architecture search. So based on the problem, you start with a range of neural net architectures, and then you have an evaluation method you set, and then you find the best neural net architecture for your data set. This is pretty much the best way for you to come up with a production model, because the neural net architecture changes a little bit every time you retrain the model. Suppose you have only one set neural net architecture that you handcrafted, right? It could be the next time you retrain the model or it sees new data, that's not the best model anymore. So you have to be able to search neural net architectures to find the best one so that you can keep on retraining. So this is very key. Again, this is one of the reasons why things are very hard to put into production, because the first time you can come up with something which works with the data that you have, and then it'll start failing 2 months later because it got a bunch of new data. Finally, explainability in models. This is the case of like, why did I see that Trump video when I was actually a Democrat? The model can now be basically, you can use a feature called SHAP, which will basically kind of expose why a particular model has a particular prediction. So in this case, for example, we're talking about a model which predicts income, and given a bunch of people, right? Like given a bunch of population, a census data which has relationship, age, education, whatnot, it kind of tries to predict whether this person has an income of 50K or more or 50K or less. And this, by doing an explainability analysis on this model, you can show that relationship is the biggest factor, which is a determinant of income. So what I'm basically getting at here is one of the big objections you will hear to deep learning is explainability. People will say, I don't know why this deep learning model is coming up with this prediction, so I'm not going to use it. The good news, if you really want to like talk to somebody like that, is to say, hey, that's fine. I'm going to use SHAP for explainability. And SHAP will help you predict the effect of the features that you put into the model. So now you know why a particular prediction is what it is. Now, explainability is a fairly new space. We can't guarantee that for every model that you create, we'll have explainability. It works for regression models, not so much for forecasting models or like anomaly detection models, but there is some work done. So explainability is going to be key to getting stuff into production. So I think the summary of what I was getting at here is, not only do you have to work at those 4 different modules I spoke about, these are the 3 different hard problems you have to find an answer to before you can provide AI as a service. Explainability, training with less data, and neural architecture search, right? And then you'll have to work on all the plumbing to get to those 4 different places. What happens if you get there? What basically happens if you have AI as a service is people can basically come, use your service to create models very, very easily or in an automated fashion. So AI represents the biggest commercial opportunity. People have said this many, many times. It's unbelievable, though. It's 15.7 trillion boost by 2030. So it's not one of those things where you're like, oh, okay, it's there. We think it's going to be as big as the internet revolution, except the internet revolution took 25 years. You could argue it started in 95, and it's still going on, so I would say to 2020. But even if you said 20 years, 2015, we had the Googles and the Amazons and the Microsofts all being $1 trillion each. The AI revolution is going to be faster. Let's assume it started at 2012. By 2030, you're going to see this large numbers of existing companies which have become AI first, but also brand new companies. So examples. So not just that I'm saying it. Organizations, this is the internet, revolution. So we don't know what the answers to the AI revolution is going to be. But here is what happened during the internet revolution, right? Organizations that didn't adopt failed. So you don't see Barnes & Nobles because they didn't really adopt really quickly. You do see Costco and Walmart, which are really old companies, but they've adopted pretty quickly. And you see a whole bunch of really new companies which are the biggest in the world being born. We think a similar kind of world is going to be there at 2030. You're going to see some companies. I feel like Samsung's one of those companies which has adopted AI, as far as I can tell. And so you're going to be one of those people most likely being AI first. And then there are companies which probably don't care for AI and they probably die. And there are going to be some brand new companies as well. So tomorrow's enterprise, this I don't really know. Different enterprises do it differently. The thesis right now is enterprises which are decentralized, control and decision making will succeed. Because you have lots of people making decisions, and each of these people are motivated by their P&L or motivated by their goals. So you don't get stuck in that centralized decision-making process, right? You have to iterate and innovate rapidly. How many times have you opened TechCrunch or anything and seen some company is going to do AI for X? Somebody is building AI for CRM. Somebody is building AI for supply chain. And the question is, there are thousands of companies which are doing CRM already, right? So why can't they iterate and innovate? And they will. So instead of having a startup come and displace an existing incumbent, what will happen is a lot of incumbents will iterate and innovate rapidly as well. And the other big thing which most companies do, a lot of, because it's easy, is to reinvent the wheel. Be like, oh, I've already, go and this person has built this in this company. I will go build the same thing in my company. That's a really bad idea. It's better to take what is there already. Just pick up whatever is already there and do something new and innovative, as opposed to just doing whatever your competitor or your other person did, because you can get ahead of them that way, as opposed to being behind them. There probably isn't a way out. You have to be AI first, meaning that when you're starting any new project, if you're not going to be thinking about how ML and AI fits into that project, it's probably going to fail in the future. It's actually about not just automating existing processes. You want to think about new businesses that only AI can enable. So you want to think about, hey, how can this expand into something new and interesting that wouldn't have been possible if not for AI? Again, the internet is a classic example. Uber wouldn't have been possible without the internet. Amazon won't be possible without the internet. And that's why they're fascinatingly new, right? Because it's not even possible to do without it. So that's pretty much it. AI so we basically, like I said, the whole thesis is AI as a service is going to be prevalent either in tools by cloud vendors, in startups, as well as internally, where people will expose an AI service which other people can use.